Welcome to the University of Michigan Dentistry Podcast Series, promoting oral health care worldwide.
Quasars, neutrons, J particles, fission, gamma rays. Most of us find these terms foreign or mysterious, but they're part of a physicist's dictionary, and they help define the world around us. We usually think of physics as difficult or demanding and consider it a man's field. Most of us don't realize that many women have found physics to be fascinating and have made significant contributions. Their love of physics stems from the drive to understand the laws of the universe. Madame Marie Curie wanted to know why certain elements gave off radiation. She discovered two new elements, polonium and radium, and shared 2 Nobel Prizes in 1903 and 1911 for her research. Lisa Meitner discovered that a nuclei could be split and determined how much energy could be given off. So began the study of nuclear power. Maria Gayapart-Mayer wasn't satisfied with a model of atomic nuclei that had been accepted in the field for years. So she developed a shell model of the structure of the nucleus. She shared a Nobel Prize in 1963 for her work. Dr. Chen Shun Wu, a nuclear physicist at Columbia University, was the first woman to be elected president of the American Physical Society. In 1957, she designed an experiment which was a breakthrough in what scientists believed about a basic physical law. Dr. Wu demonstrated non-conservation of parity, which means that the physical laws which govern a system of molecules are different from the laws which govern the mirror image of that system, like the difference between the right and left hands. In other words, nature is not always symmetrical. In 1983, Sally Ride became the first American woman to explore space. Her PhD in astrophysics helped her as flight engineer to perform experiments outside the space shuttle using a long remote manipulator arm. All these women have one thing in common. They're curious about nature and the universe and want to find out how and why things happen. They may be interested in the tiniest aspects of our own world, or they may be interested in the huge spectrum that is the universe. Physicists and astronomers take nothing for granted. There's always something new to learn. Linda Verdoorn Powers is a theoretical physicist for KMS Fusion, a research organization. She wants to know how we can develop new energy sources by harnessing the power of the nucleus through laser fusion. Linda is currently completing her PhD in plasma physics at the University of Michigan.
What I do is try to understand what's going on in laser fusion experiments, and that means sometimes developing theories of general problems that occur in all fusion experiments. Fusion is trying to combine 2 light elements, in our case 2 isotopes of hydrogen, into a heavier element. Laser fusion just means that the way we try to get this process to occur is by shooting a laser at this hydrogen fuel and compressing and heating the fuel until it gets to temperatures and pressures where this fusion, combining of atoms, can take place. Yeah, the goal of the laser fusion experiment is to generate more energy from the fusion reaction than you use to cause the reaction, and at that point, collect that energy and convert it to electricity. And hopefully this would give us a very clean and endless source of energy, because the fuel for fusion is very common. The nuclear power now is produced by fission, which is splitting heavy atoms into 2 lighter atoms. Fusion is combining 2 light atoms into a heavy atom. Both of these processes give off energy if you choose the right elements. the amount of energy contained in a fuel capsule is so small that there's no possibility of a runaway reaction. We believe that there would be less radioactive waste from the fusion reactor so that the waste disposal problem would be solved. The fuel, which is hydrogen, is very common in seawater, so there's no shortage of the fuel. I had a master's in math when I came to work on this laser fusion experiment, but I had actually been interested in physics as far back as high school and early college. I started out as a physics major in college and was sort of sidetracked by some lack of encouragement on the part of some of the faculty members. But after I got involved in working at KMS, I just decided I wanted to be more in the mainstream of the problems they were doing. And so I decided that to be in the mainstream, I really needed to become a physicist, and I found the field exciting enough to make the commitment to do that. And overall, I think what I'm doing is wonderful, and there are lots of days when it's very exciting and very satisfying. I've discovered something, or I've explained something, and I'm on top of the world. And there are also days when I'm beating my head against the wall, and I don't think I'm ever going to figure anything out again, and then it's very frustrating. But I guess the satisfaction of finding the answer outweighs the frustration of looking for it for me.
Many physicists find jobs in research with government agencies. Jun Rooks, who has her master's degree in physics, works for the Naval Weapons Center in California. She has worked on several major projects at the center, including the evaluation of a new jet's performance and how accurately it delivers weapons. June had polio when she was 2 years old and did not start school until the 4th grade. She was the first disabled woman to graduate in physics from her university. Her disability has not prevented her from pursuing a successful career.
I work on a simulation of the operational flight program that is in the A6E aircraft. The computer program really is the brain of the aircraft. All the weapon systems in the aircraft is in the computer program. And my job is to work on a simulation of that program. I envision it as a small aircraft in a little small world that's in my computer. And I think it's a lot easier to solve problems on the simulation. And then if you want to make changes, you first make them in the simulation and then make the change in the flight program. I'd like to learn a lot more about the weapon systems of the A6 aircraft. And I can see myself growing in this area and working at least for another 5 years. It's just so much to learn. I work with other physicists and analysts and computer programmers, mathematicians. We kind of work together. I use a lot of classical mechanics. I use just about all of the physics I learned in undergraduate and graduate school. I learned a lot of theory, and now I'm really trying to put that theory to work. And I find that it's quite a challenge. It's difficult, but I work with a wonderful group of people and a lot of experts, and it's really, really just a good atmosphere. I believe that my job is important because I work for the Department of Defense, and defense of our country really means something to me personally. Therefore, I consider it an honor to work for the Naval Weapons Center and also the Department of Defense. I like my job because I like solving problems. I think my job is fun because I like the people I work with, and I just like math and physics. So when you can combine all these things, I think it's just happiness.
One of the most controversial subjects in the news in recent years is nuclear power. A nuclear physicist not only studies areas associated with nuclear power, she also explores effects of radioactivity upon the environment. Radiation is being utilized with great benefits to mankind, but it also has the potential to damage living organisms. Nuclear reactors, X-ray machines, and radioisotopes used in research and medicine present hazards because of their ability to irradiate and contaminate human environment. Health physicists try to protect humans and their environment from potential radiation hazards, and at the same time make it possible for us to enjoy the benefits of using the atom. Health physicists may work in federal or state agencies, industry, hospitals, or universities. Betsy Tanner is a nuclear physicist at Emory University in Atlanta. She has her bachelor's degree in physics and a master's degree in medical science. This combination has allowed her to work both in the health and environmental sciences.
We do an environmental monitoring program for, right now, a nuclear power plant that's being built. We started the project before it was in operation, so it was called pre-operational environmental monitoring. It went online last summer, so it's now putting out electricity. So now we're doing kind of follow-up studies just to see if they're contaminating the environment at all with radioactivity. We are basically just the analyzing end of it. The samples are collected by power plant people. They have set up 6 test gardens, they call them, and they grow through a regular growing season, receiving what care a typical garden would receive, and then they sample the fruits and then the leaves as another measurement. And they don't send us fresh tomatoes, unfortunately. They send us dried tomatoes. But then we count the different fruits from the crops just to ensure that there's been no radioactivity released by the plant and taken up, released by the power plant and taken up by the crop itself. You have to know a good bit about nuclear physics. Basically, my basic training was in nuclear physics. Environmental monitoring incorporates the nuclear physics training. I have to know what radionuclides I'm looking for and know how to write the equations to get the correct answers to analyze the samples. My job is fun. Part of it, the reason it's fun is because it's so varied. It's also a fairly rewarding job in that the environmental monitoring is something productive to society. We are saying, yes, you are doing a good job. You have not contaminated the environment.
Some physics specialists take another career path. Gail Aider, who has a combined master's degree in education and physics, teaches high school science classes in Louisiana. Gail is one of many scientists who is drawn to the classroom because they want to share the love they have for their fields with young people.
I think that physics is important for students that are college-bound, not just for learning the physics, but for learning the thinking skills involved in physics, learning the problem-solving techniques. It is the first chance that many students have of actually seeing the practical application of their math concepts. You know, they take Algebra 2 and they learn how to graph a hyperbola and a parabola and an ellipse, etc. But they don't understand why they ever need to really do that. In physics, they use those math concepts. And I think that it just hones their math skills and makes them much better at truly solving problems rather than plugging numbers into formulas. A good measure of common sense will get you a long way in physics. You know, I started at the beginning of the year asking them some questions that anybody with any common sense knows and understands. And I say, well, you already understand physics. And a lot of it is just common sense. You know, if you've got a car parked on a hill and you forget to put the emergency brake on and it starts rolling down the hill and you run out of the post office and see it, you know, you hope you're driving a Volkswagen and not a dump truck, because a Volkswagen will be easier to stop, right? And that's a principle of physics. If you understand that, then you won't have any trouble with physics. I think we need to change the way we're teaching science in the classroom. We need to talk about those everyday things that are so important. They need to know about genetic engineering and nuclear energy and MX missiles, etc. Because they need to develop an awareness and appreciation of science so that they can make wise decisions as adult citizens. It's important for everybody to understand science and appreciate it, whether they're going to be a scientist or not. I was a terrible student in high school. I made an F in advanced math, an F in chemistry, and an F in algebra 2. My parents wanted me to be an intellectual, and I wanted to party and have a good time, and I rebelled. I would love to be able to go back and do it all over again. I would make straight A's, and I tell my students that. You know, you can't go back and do it over. Do it right the first time. And they say, Miss Aider, you were so bad. Why do you fuss at us when what we do is nothing compared to what you did? And I'll say, you know, because I don't want you to make the same mistakes that I made. I always want to be involved in education. And I always want to be in the classroom. I would like to get involved in the development of educational materials, find new and better ways to do it, and communicate these ideas to other teachers. So I want to be a classroom teacher, but I want to do other things in addition. It's fun. I wonder sometimes why they pay me money to do it. I can't think of anything else that I would want to be doing. This past spring at the National Science Teachers Convention, I received the Outstanding Science Teacher of the Year Award, sponsored by Discover Magazine. And the award was a $5,000 cash award, which was real thrilling. Then, last week, I was notified that I had been selected a Presidential Award winner for excellence in science and mathematics teaching. And this award includes a $5,000 grant to my school to be used to supplement the science and math program, and also an expense-paid trip to Washington and a White House reception where the President will present the award.
A field tied closely to physics is astronomy. Whereas physicists often look inward at our own world and the nuclei and molecules that comprise it, astronomers look outward beyond our known world. Will the universe expand forever? How are stars born and how do they die? What other worlds and universes are out there? These are just some of the questions that astronomers are trying to answer. Anne Cowley and a colleague recently discovered the second black hole in our universe. Dr. Cowley has a PhD degree in astronomy and conducts research while on the faculty of the Arizona State University.
An astronomer studies about the universe. Everything from the motion of the moon, what it's made of, out to the most distant galaxies. And, well, this is hard because people always ask about why astronomy is important. Astronomy is that basis. We want to know where we came from and where we're going to. It isn't going to make better mousetraps or it easier to earn a paycheck. It's really understanding about the nature of the universe. Right now, most of the work that I'm doing is in Chile, so I'll go to South America. In the afternoon, you have to get the equipment ready and test it and make sure everything is ready to go. As soon as it begins to get dark, you've got to go up and really get the telescope ready, open the dome so it can cool off, and get all of the computers and everything going. And then you work until it's dawn, unless it happens to be cloudy, which it never is in Chile, fortunately. You don't look through the telescope anymore, or rarely. Occasionally, when something's broken, you have the chance to go sightseeing and look through the telescope. But mostly what you do is you have a program that you've planned ahead of certain objects, maybe some galaxies, maybe some stars, maybe some planets, that you want to make some particular kind of observation of. Maybe you want to find out the color that that star has so that you can determine its temperature. You have special kinds of detectors that will then be able to make measurements once the telescope is set on the star. Then to make sure that all of the computer equipment or whatever, almost everything is done with computers nowadays. And so we take the data and record it on magnetic tape. A black hole is thought to be a star which has collapsed to such a small size that it has intense gravitation so that nothing can escape from it. If you were to take a star like the sun and collapse it to a very, very small size, then not only could no matter escape, but also no light can escape. And that's why it's called black, because any radiation or light that's given off from a black hole is prevented by the very strong gravity from ever leaving the surface of the object. The way we discovered it it was by accident. We were trying to study stars in the nearest galaxy to our own, which is called the Large Magellanic Cloud. And we had a very set idea of what we expected. And the first night we started making the observations, it didn't fit. And my colleague David Crampton and I said, gee, I wonder if it could. No, it couldn't be. You don't even say the word. So the next night we went up to the telescope, and it turned out that the period was too long to be a neutron star. The only thing that could explain the observations was a black hole. So by about the second or third night of making those observations, we knew that we had it. And it was funny, because at dinner time, the other astronomers are all sitting around, and everyone sort of tells what they're doing. And we thought, gee, we're going to look silly if we say we found a black hole, and then we get home and study it, and it isn't. So we just kept our mouths shut. But because if you make one mistake in presenting your observations, then that throws doubt on anything else that you've done. And both of us have worked a long time, and we didn't want to be wrong and have our credibility sort of spoiled. So we were very cautious about it. It was really fun. Astronomy is really interesting. I mean, if you had to ask what science really tells us the most interesting stuff, it's got to be astronomy. You're finding out things that are happening at the edge of the universe, what's happening at the beginning of creation, at the end of all times. You have the opportunity to ask questions and then try to answer them. You're really your own boss. I mean, what you do is limited only by your own imagination.
Although physics and astronomy can be extremely demanding, some women in these fields combine their family lives with their careers and hobbies.
When I first got married, I think I believed that I had to be everything my mother was and everything every woman on TV was, and have a career on the side. And you find out very quickly that that just doesn't work, and something's got to give. So you decide what's important and start making changes. And
you have to give up certain things when you have a two-career marriage, I believe. That, you know, I think we both agreed that, you know, we're just happy giving up. Like, you know, we don't have gourmet meals every evening, for example. You know, we're both very busy. We do a lot of other things besides our careers. We like to do a lot of athletic types of things, play golf, and we're both very avid runners. So I think it's very simple that in terms of supporting Linda's career, it's something that she is very interested in. That is what really gets Linda excited and gives her a sense of satisfaction and reward is pursuing her career. You know, I don't see what difference it makes whether you're a male or female in terms of expectations. You know, if you have the gumption like Linda does to become, you know, a very top-notch person in your field, I'm all for supporting that person, regardless of what sex they are.
I think both of my boys are glad that I've had a career and think that science is interesting, although neither of them particularly wanted to do that. Particularly with this recent black hole discovery that's gotten a lot of news media. They come home just beaming from school when their science teacher says, "Is this your mom?" and holds up a newspaper article.
I enjoy this job because I can work it part-time, and I have a very flexible schedule. I think it's enjoyable to be able to combine both home and career. There's certainly, to me, nothing more important than having a child and rearing that child to enjoy life and be a good citizen and responsible person. But I don't think that that is all we women have available to us. I think that we can contribute in the workforce and at home. It's sometimes a bit of a juggling act to do both, but I certainly recommend it.
A career in physics or astronomy usually starts with a bachelor's degree, but most physicists must continue on in school to receive a master's degree or PhD degree. A master's degree usually requires an additional 1 to 3 years, and a PhD degree takes an additional 3 to 6 years beyond the bachelor's degree. An advanced degree usually enables you to hold a job with more responsibility and a better salary. A college major in physics is a good foundation for many careers, such as engineering. Most physics majors begin with general physics courses, then take more advanced courses in specialized branches of physics, such as mechanics, electronics, thermodynamics, acoustics, atomic or solid state. Since laboratory work is essential in physics, it is important to take every opportunity to acquire skills in working with mechanics and lab equipment. Courses in computer science are very useful. Many students also find it helpful to get some job experience related to their field of study. More information about academic preparation, career opportunities, specialties, and salaries can be found in the brochure that accompanies this videotape.
Most higher institutions give advanced placement tests when a student enters college. And students can elect to take these tests in their foreign language or in mathematics, in chemistry, in physics. And it's a test that if they make a high enough score on the test, they are given credit for the first course in that subject, or maybe even the first 2 courses, and they go on and start at a higher level in college. And when you talk about the expense of college today, that's very important. I think that students should take all the math and science they possibly can in high school, whether or not they plan to be a scientist. Most students in high school don't know what they want to be when they grow up. And for that reason, I think that they should leave all doors open.
In high school, I think anyone who's interested in any science should take math. I mean, learn math, go through all the head pounding in high school so that it isn't a problem. You know, it's like if you were going to go to France, you know, you'd spend your time here learning the French language. And then once you learned it, then that's not a problem, you can use it. But take as much math as possible, because you don't want to sit there trying to, you know, struggling to learn that. That should just be something that you can draw upon with ease. I mean, something you should be very comfortable with.
I'm studying an area of physics that's called quantum physics right now. And I find that very fascinating because it deals with all these things that I find hard to believe. And it's really fascinating to me that people who know more than I do can actually believe these things which seem so ridiculous and incomprehensible. It's like the one theory that we learned today that our teacher was telling us that almost caused anarchy in the class. It was like, but how can you say that? You know, this is a real uproar from the whole class, was that if you have a particle and there's a chance that it might be over here, but there's no way that it could have gotten there, was sort of basically what it seemed like he was saying. And sort of, but how can it maybe be there and not ever have gotten there? So it's things like that that are very fascinating, just the whole incomprehensibility of it. Physics is just like you have philosophers who try to figure out how things work and what the universe is. Physics is a way of trying to understand how things work and what the universe is, and you use math as a tool of helping you understand what the world is. And that's why I liked physics, or I like physics, because it helps me understand things.
Well, I have a project right now for this term, which I started in the summer, which is building a gas chamber, essentially. What that is a box filled with a neutral gas, an inert gas. There's no charge in it. And then I have wires strung through this thing very tightly. And when particles come through, they ionize the gas. They ionize it locally. They knock off electrons or whatever. And this charge, extra charge, is picked up by the wire and sends a signal, propagates a signal down the wire. It's picked up by the electronics. So what this tells you is that something has gone through. Now, what I'm building is a relatively crude device. It's not going to tell you what has gone through. It'll basically tell you something has gone through and how intense it was. And that's about it. This is going to be a prototype for hopefully hundreds, thousands of these things that they're going to build and put all over a mesa someplace in Utah. It's going to be part of a cosmic ray experiment. Cosmic rays are anything that comes into the atmosphere from the outside universe.
I worked in a solid-state laboratory for a really wonderful professor and all these very helpful graduate students who, if I had any questions, they would help me. And I set up different experiments and ran them and made things and made different samples. It was just a really fascinating job and kept track of things, and it was a lot of fun. It's valuable because not only does it give you a sense of what type of work you're going to be doing in physics, but it also tells somebody else that you are interested enough to spend your summer working. For me, it was just, I learned so much about what science is really like by doing this work, much more than I had learned academically. Just about how many times you have to redo an experiment and how much frustration there is in setting an experiment up which doesn't work, and how much help there is among scientists and in cooperation.
Physics and astronomy are challenging fields that seek to answer some of our most important and baffling questions. They study the laws and properties of matter, motion, heat, light, and electricity to develop an understanding of our physical world. These scientists are intrigued by the wonder and harmony of our universe. They want to learn more.
You've been listening to a presentation from the University of Michigan School of Dentistry, which is dedicated to supporting open learning and open educational resources. This recording is licensed under the Creative Commons. It may be reused and redistributed for nonprofit use. Please attribute materials to the University of Michigan School of Dentistry and redistribute under this same license. For more information on how this and other University of Michigan School of Dentistry recordings may be used, visit www.dent.umich.edu/license.